I gotta say it carefully because the brain develops all throughout life, right? But when we talk about the foundation of the brain, when it all comes together at the foundation, is what you got, okay? But the brain, no matter how old you are, you can still learn new things. Makes sense, right?
Yeah.
It's just you learn things slower. Remember, every time you learn something new, your brain is developing. It makes sense, right?
Mm-hmm.
Because, you know, just think about it. You know, we talked about it earlier, but skills are, yeah, here you go. Remember, every skill that you have has a particular pathway. Understand? Your ability to chew food, right?
Mm-hmm.
Your brain's involved and pathways are built around chewing food. Makes sense, right? So that's why you can see and get hungry, right? You can smell and get hungry, right? Because your brain is connected to all these things to help you live and do better. If y'all start learning brain science like I want y'all to do, your brain pathways are built around the knowledge of brain science. Makes sense, right? Math pathways, word pathways, exercise pathways, right? It all has to be working for you to get skills in those areas. It makes sense, doesn't it? Understand you can lose skills in some of those areas, and the brain will compensate to that, right? So I'll give you an example, just you know, if a person is born being able to see, suddenly they have an injury that causes them to be blind, what happens is the brain begins to put together visual, touch, movement sense to make up for it. So for instance, I can look at y'all and tell that he's over there, he's over there, he's over there, he's over there, right? When I lose my sight of that, I depend on hearing a lot. So I can tell when you're on the right-hand side just by my hearing without being able to see, right? All right, so close your eyes for me, I'm gonna show you something. All right, close your eyes, don't cheat. What does that sound like?
Knock.
There you go, but okay, keep your eyes closed. What does it sound like?
Tap.
Right? Okay, how do I make this sound? Keep your eyes closed. How do I make this sound?
With your hand?
Mm-hmm. How do I make that sound?
The finger.
Maybe marker or something?
All right, so somebody said finger, somebody said marker. Now you understand, now you can close, open your eyes. So now you understand, you can hear differently. So my first time was this. Second time was this. Somebody in their memory has heard a finger knock on something that sounds like that. So they said finger. You see how you accumulate this information, but you can interpret it differently. That makes sense? So if I become blind, I walk in to do the lecture, I don't have to see the word. I can put it on a record and hear it and know what I want to tell y'all without even seeing the words. But I can still teach without no eyesight. Make sense? Your brain knows how to do that. It does it. Right? Right? You see how some people, they can hear things better than you can? Right? Women tend to hear the sound in words better than we can. Right? Makes sense, right? It may not make sense unless you know about that corpus callosum up there. Children are better at hearing some things in sound than we are. Right? All right, so the point is,
Excuse me, I had to move.
Okay. So the brain develops from back to front.
See that.
Got it? It develops from back to front. And it's building skills all along the way. Makes sense, right? Right? Because kids don't really start talking until about 2 to 3 years old. I'm talking about we can understand. Right? So it makes sense, right? So when you begin to understand this, what I like to say is kids can pee and poop, then they walk and they talk, okay? Then it lets you know, this develops first, because they can pee and poop, right? Then they get more skills on how to control this, right? Right, so potty training, right? Potty training. That's building skills of potty training. So the brain develops around potty training, right? Understand that some people get spinal cord injury, brain wound, they can't control their bladder no more. Because they've knocked that pattern out. You see how that works? They've knocked that skill pattern out. It makes sense, doesn't it? And when you talk about back and forth, pattern building, new patterns being built all the time. Brain injury can interrupt the normal pathways and patterns, okay? All right, so we're gonna hit this video here, and we're gonna get in more detail, and we're gonna talk about 17 different parts that are in these zip codes, okay? All right, here we go. Then we come back and talk to them, we call it. All right.
Hi, it's Mr. Anderson, and in this video, I'm going to talk about the brain, structure and function. Remember, structure is what it's made up of, and function is what does it do. We sometimes refer to this as the anatomy or structure, the physiology, or the function. And so the cool thing is that we're going to go through 17 different structures in the brain, kind of lay out the basic plan of the brain, but you're using your brain to process it. And if you do a good job when we get to the end and I review all the parts, you should be able to tell me what their structure is and what their function is. And so what type of organisms have brains? It's the animals. Animals use nerves, they have muscles to move around, and so they have to organize that movement, and so they use a brain. And so if we look at the two basic body plans of animals, some are radially symmetrical, in other words, they're built around almost a tire, and then some are bilaterally symmetrical. In other words, a tiger, you could draw a line right down the middle, there's going to be a clear right side and a left side, there's going to be a clear front and end. And as we became bilaterally symmetrical, we had to organize that movement. So this is a simple animal body plan. And so this animal is going to move towards the right, and as it does so, it has to take in information. We call that sensory information using neurons. And so right now you're taking in sensory information from your eyes, from your ears, and then inside your brain, you're going to integrate that information. You're going to make sense of it, and then you're going to figure out what you want to do, how you're going to act dependent upon that. And so then we have this loop of motor neurons out, or motor nerves. And so this loop in simple animals is also important in understanding how our brain works. But if we look at these real primitive brain, we find that they have a real common structure. They have these 4 humps, and we call those the first one's not a hump, but the spinal cord. We then have the hindbrain, the midbrain, and then we finally have the forebrain. And we find this consistent throughout all animals. And if we look at something like a shark, it pretty much looks just like that primitive brain. You can see down here we've got the spinal cord that's bringing information in. We then have the hindbrain, the midbrain, and the forebrain. And so one thing you should remember is that the closer we are to that spinal cord, the more basic the functions are. And so we're right down in this hindbrain, it's going to be basically keeping the heart beating, keep the circulation going, digestion in the shark. But when a shark decides to attack you, or it has some kind of an emotional response, that's going to be way up here in the forebrain. Now, if we look at you when you were really little, when you were an embryo, you had a brain that looked very similar. You had a spinal cord, you then had a hindbrain, you had a midbrain, and then you had a forebrain. But during development, that brain changes radically. And so this is what an adult brain looks like. So we still see that spinal cord. We then have the hindbrain, we have the midbrain, but look how large that forebrain is going to be. And so that's where all of those emotions and memories and all of that thinking we generally attribute to the brain is going to be in the forebrain. And so let's get to the actual anatomy. And so there are going to be 17 parts that we're going to go through. So you should always be thinking, what's the name of the structure, where is it, and then what's the function, what does it do? And so if we look at a basic brain plan, we find these 4 things jump out right away. We're going to see the brain stem. We then see a cerebellum on the back of the brain. So again, to get yourself oriented right, the eyes are going to be right up here. And so this would be towards the back of the head. So that's going to be the cerebellum. We then have the area of the thalamus, hypothalamus, and then finally we have the cerebrum, which is going to be that dominant upper portion of the brain. And so let's begin with the brain stem. The brain stem is broken down into 3 individual structures. So if we start at the bottom, we've got the medulla oblongata, the pons, and then we finally have the midbrain. And so those 3 things, medulla oblongata, pons, and midbrain, make up what we call the brainstem. So that's the structure. What's the function? Well, it really does 2 things. The first thing it's going to do are these more basic needs. It's going to keep your self-breathing, keep circulation going, digestion, swallowing. All of that is going to be controlled by the brainstem. If there's any damage to the brainstem, it's going to be catastrophic. What else does it do? Then we have information coming in. So we have sensory information, just like that worm did, coming up to the brain. And then we have motor nerves going out. And so the brainstem is important in routing that information and filtering that information, sending it where it needs to go. What's behind that? We have the cerebellum. The cerebellum, and the function of that is motor control. So as you do sports, for example, it's the cerebellum that's giving you that coordination. And it also gives you motor memory. So as you learn to ride a bicycle and you remember how to ride a bicycle, that's going to be thanks to your cerebellum. If we keep moving up, we now have the thalamus. The thalamus, again, sits right on top of the brainstem. And so the best analogy I could come up with is a router. It's basically sorting data and sending it where it needs to go. If we were to look below that, there's a little structure here that's incredibly important. It's called the hypothalamus. It's going to be really right above the roof of your mouth. What is that accountable for? It's homeostasis. So it's maintaining body temperature. It's maintaining osmolarity. All of that stuff is contained right up in the hypothalamus. Also important in circadian rhythms. And then if we look right below that, you can see a little gland hanging out. And 1/2 of that pituitary gland, the posterior pituitary, is technically part of the brain. And it's important in basically sending off hormones. And so there are nerves that flow into that pituitary, and it's sending out things like antidiuretic hormone that keeps your water balance the same. Oxytocin would be another important hormone that comes out of there. If we keep moving up, then we get to the level of the cerebrum. What's the function of the cerebrum? That's integration. So what we're doing is making sense of all that data that comes in. Now, what makes up that cerebrum are going to be all these neurons. There's tons of neurons that are connected together, billions of neurons and billions of synapses or connections between these neurons. And that's where we're making sense of information as it comes in. Now, if you were to look at this image right here, so of that brick wall. So take a moment to look at that, and I'm going to show you some other images. Now focus on this, and then that, and then that. And what we find is as you look at those images, your brain is integrating. It's making sense of all that information. And it used to be a black box. We didn't know really what was going on, but now we can use technology like a functional MRI. Functional magnetic resonance imaging. And what we're looking at here is a brain in action. So this same study was done on females, and what they would show them is something neutral, like a brick wall, and then a kitten, and then something like dirt, and then something like puppies. And so what we're seeing is as those images are switching back and forth, we can start to see where blood is flowing around in the brain, and we can start to figure out what the different parts of the brain actually do. We're able to figure out their function. So when we're looking at the cerebrum, every picture that I showed you is from the side, so the eye's up here. But if we were to rotate that 90 degrees, now we're looking at it head on, we'll find that there are 2 hemispheres. There's going to be a right and a left hemisphere. Now they're connected in the middle using something called the corpus callosum. So that's a connection of nerves in between the 2 hemispheres. And we do tend to show lateralization. There are going to be certain things that we put kind of on the left side of our brain, like mathematical reasoning and logic, and things that we put on the right side, like facial recognition. Now this is plastic. In other words, we can move these functions back and forth. And you can even have a radical hemispherectomy where you're cutting one of these out and you still have a functioning brain. Now, if we were to go right below the corpus callosum, we get into this area called the basal ganglia, and it's made up of a bunch of nuclei. What are nuclei, or what is a nucleus in a brain? It's basically a bunch of neurons that are right next to each other that have the same function. And so all of these nuclei together make up what's called the basal ganglia. And you can see this would be the corpus callosum connecting it together as well. So this is below the cerebral cortex. What's the function of that? Well, scientists have been able to figure out this complex interaction of inhibition and excitatory response between these neurons, and basically it controls a lot of our motor control. And if you have somebody who has Parkinson's disease, then we're having problems in this basal ganglia area. As we move farther up the brain, we eventually get to the cerebral cortex, and that's going to make up about 80% of the brain. So it's most of the brain itself. And it's broken apart into these 4 lobes. And so if we start in the front of the brain, we have what's called the frontal lobe. What's the function of that? It's mostly executive function. So it's kind of like the boss of your brain. It's emotional control up there. And if we have people who have damage to that frontal lobe, they have really huge emotional swings. As we move back towards the back of the brain, we get to the parietal lobe. What's the function of that? It basically is sensation. It's you dealing with and reacting to your environment. So we have a lot of neurons coming in here from sensory input. As we move to the back, we have the occipital lobe. The function of that is vision, primarily vision. And then we move onto the side, we have what are called the temporal lobe. Temporal lobe is going to be important in language, it's important in hearing, it's also important in memory. We have a lot of memories in there. And so each of these lobes have different functions that are associated with it, and hopefully those little icons help you remember those functions. Now, if we were to go inside the parietal zone, we'd find a really important part here. It's called the somatosensory cortex. And that's where sensory information is coming into the brain. And then on the other side of the lobe, we have what's called the motor cortex. And so going way back to that worm, we have information coming in, sensory information, and then we have motor output coming out. And so that's going to be a point of integration where we get information in, decide what we want to do with it, and then send that message back out. Now, if we were to look at that somatosensory cortex and map it along the cerebral cortex, we would find that we dedicate huge amounts of that brain surface area to things like your fingers, your tongue, your lips. In other words, we have way more neurons and way more sensory information coming in from your fingers as opposed to, for example, your back. We don't have as much of it dedicated to that on the backside. We could also use functional MRIs and then even an operation to figure out where a lot of these things are located, like speech and smell and hearing. But over the future, we're going to get really, really good at figuring out specifically what are all the different parts of the brain, what are the nuclei, what do they do, and even mapping it down to the level of the neuron. So how did you do? Do you remember those 17 different structures and their functions? Well, it's time to review. So let's go through it. What's this one at the bottom? Overall, we call that the brain stem. Hopefully you got that. What are the 3 parts of the brain stem, though? Do you remember that? Could you pause the video and then say what they are? Well, starting from the bottom, remember, we have the medulla oblongata, we then have the pons, and then we have the midbrain. So that's going to be the structure and where it's found. Can you remember the 2 functions of the brain stem? 2 big things were, number 1 is to maintain breathing, heart rate, digestion, swallowing, so these fundamental properties of life. But what's the second one? Remember, it's to sort information going up and down. What's behind that? What's that structure called? That is the cerebellum. And so what's the cerebellum do? Remember, that's coordination, motor control, and also motor memory. Do you remember what sits right up above the brain stem? That is the thalamus. What's the thalamus do? Remember, it sorts information as it moves up to the upper parts of the cerebrum. What's below that? That is the hypothalamus. Underneath that, what's that do? Remember, that's homeostasis. It's maintaining that internal body state. Do you remember what hangs out the bottom of that? That is the posterior pituitary. Hopefully you're doing well so far. If we keep going then, what is this upper portion of the brain called? We call that the cerebrum. Okay, let's keep going into the cerebrum then. So do you remember what's that connection between the 2 hemispheres of the brain? We call that the corpus callosum. And do you remember what we call those little nuclei that are found below that cerebrum? Those are called the basal ganglia, and they're really important in motor control. And remember, the corpus callosum allows our hemispheres to connect. If we were to go up to the upper portion, what do we call this highly folded upper portion of the cerebrum. That's called the cerebral cortex. Do you remember what the front lobe is called? That was pretty easy. That's called the frontal lobe. What about the yellow lobe right here? That's called the parietal lobe. Do you remember what they do? Frontal lobe, remember, is executive or boss-like functions, and then parietal is going to be sensation of the environment. What about at the end? Do you remember that? That's called the occipital. And then what about at the bottom? That's the temporal. Occipital, remember, is a location where we have vision, and then temporal is going to be more language, hearing, memories are there. Now there are two other parts in our lobe. So what do we call this area right here, and then this area right here? Those are called the somatosensory cortex. Remember, that takes in information, makes sense of it, and then we have the motor cortex, which is sending information out. So those are those 17 structures. If you don't remember them, you may want to watch the video again, maybe make some flashcards.
Okay, all right. Give me some points that you got from it. Yeah, good. Give me some points you got from it. Just don't. When I try to, don't worry about the big words. Just pick out what you got, what you can understand.
There's 17 parts in the brain.
See, there's 17 parts of the brain, and what I like to call them, they're in 3 big zip codes: hindbrain, midbrain, forebrain. Just like you got zip codes, you got plenty. You got buildings, you got everything else within them zip codes, right? And the 5 stations, the whole thing. So I just give big 3 zip codes, and then you put what's in those zip codes and figure it out. What else you get from just simple stuff? All right, don't worry about
Spinal cord.
Spinal cord is pretty important because that's the big gateway to receive information from everything else, from your muscles, the way you're moving, the thumb up here, and all that kind of stuff. So if anything happen to that, that's a major part of the hindbrain's function. You're not gonna do nothing without that spinal cord being intact.
Back up control your motor skill.
Say it again? Yeah. Understand, you got this big cerebellum, that's most muscle coordination. But remember now, what I like to remind myself, a lot of information comes in those areas, but it ain't gonna do nothing, everything else is connected. If everything else getting connected, you're not gonna do anything. So with the motor cortex, has to be connected with the cerebellum through the spinal cord for anything can happen. Anything happen along that, you're not going anywhere. Right?
The back of your head is your vision center.
Yeah, I'm talking right back in here is visual centers. But remember now, visual centers connect to everything else.
Yeah.
That's the optical.
Spinal cord connects to your brain.
Yeah. It just told you big old pathways. Yeah, because it's a continuous path. For instance, you got nerves. One single nerve that goes from the tip of your toe all the way up to your brain. Through the spinal cord. And so it's located in the spinal cord. But remember, it's got to take information all the way up from your toe to your brain. You got single nerve cells that are long, right? Remember now, your sensation going 225, 250 miles an hour, so you get there pretty fast, right? It ain't if you're going 225 miles an hour from here to there, that's pretty quick. So what you see me doing here, right? Going 225 miles an hour. The sensation, the electrical charges are moving that fast. So I can do that. It's almost instantaneous, right? Yeah, like all that noise comes to my ear. That's 225 miles an hour. So
I can hold my hand, I know where it's coming from.
All right, anything else you get from it? What else you get from it? Just any factoid.
The hypothalamus takes care of homeostasis.
Yeah. That's extremely important to understand. Hunger, sense of thirst, right? So if you knock that out, so some people with Alzheimer's disease, that thing get knocked out. They don't want to eat, they don't want to drink nothing. Depending upon where, and the hypothalamus is damaged. Right? Understand that?
An addiction, also that hypothalamus will make you worried. That's me where I don't want to eat or drink.
Yeah, because you've taken it offline, so its function when you are taking an addictive substance, it compromises the balance between you desiring food versus desiring the drug. Makes sense, doesn't it? Make sense?
Amen.
Yeah, somebody in the church. It ain't sleep. All right, so yeah, you see that? So again, when you knock your brain off balance anyway, you can lose the function of the other parts of the brain. You ain't thinking about eating when you strung out on drugs. All right?
Some parts of the brain can be removed. Some parts can work for other parts.
Yeah, because that's the other important point is
To reroute.
if you knock out a whole part of the brain, like, well, let me just say it this way, there is certain seizures, extreme seizures, that fire only on one side of the brain. One way to help those folks is take that part of the brain out. The rest of the brain would try to adjust to that.
I seen where, some doctors disconnected a girl's, parts of her brain, was, it was majority of it.
Yeah.
To keep her from having daily seizures.
There you go. That's the point I'm making. So, because
Wouldn't
there's some
wouldn't that affect her so much though?
Yeah, it does, because sooner or later, so whatever side the seizures are, the opposite side is affected, right? So the muscles get weaker on that side, but you still can use your muscle. You understand that? Because the way we're able to keep symmetry, muscles equal on both sides, right? We got both sides of the brain working. So when we exercise, right?
Right.
Right? So both sides of the brain are working all the time. Understand, and notice, check this. Notice that tennis players who are right-handed, the right arms are bigger than the left arm. Remember that? Now some preserve the symmetry, but most times one side is bigger than the other. Depends upon, right hand, left hand playing tennis, right? By the way, here's another little factoid. Some people that do this, they can put you on a scale. The scale is made, when you're centering yourself, you can weigh one side or the other side. Whatever, and I forgot the ratios, but whatever side, if you're left-handed, this side of your body is bigger. If you're right-handed, this part of the side is bigger. You can understand why, right?
So if you
The muscle mass over here is bigger because
working more.
exactly, right? You're gonna use whatever side you are, you're gonna use that side more, right? So there's more pathways for activity on the side that matches the brain. Make sense, right? Make sense? So, yeah, okay. If that was on a little bit, what part of you don't you understand? But you get it, right?
Mhm.
You get it, right? So right hand, if I'm right-handed, this side is gonna be heavier. If I'm left-handed, this side gonna be heavier, right? All right, makes sense, right? All right, so, let's see what time it is.
20 minutes.
All right, okay, good. So, see, what else I wanted to say? Oh, notice that he put things in the midbrain that I didn't put in there, okay? Now, the reason why, even though he looks like he put in different things, remember the idea of it all connected, right? Remember muscle coordination, a large part of the information in the cerebellum, right? Didn't he show you that spot right below the corpus callosum that has, what's the name of that thing? Oh, I just forgot the name of it. Let me see if you got it up there. 'Cause I
It's
forgot
called the lateral vent,
No.
right below the core.
No. Can you give me the front view of the brain? Because I forgot what it's called. Oh my goodness. Anyway, that also is connected with the cerebellum, right? In Parkinson's disease, you got a problem in the cerebellum, and you got problems up there too, right?
Mhm.
So that's part of your muscle coordination system, even though a lot of the information comes through the hindbrain. You see what I'm saying? Because that's up in the forebrain. Now, it makes sense, right? Because your forebrain got to figure out what's going on, right? You got that. The cerebellum interprets what's going on, right? It has to come through the hindbrain, through the midbrain. The midbrain helps send information to where it's supposed to go, like the whole router thing. You got the router, right? Because in your home you got a router, right? So you can go to your phone, you can go to your tablet, you can go to your computer, go to your phone line, right? And it depends on what you're using most of. That's where most information gonna go. Makes sense, right? That makes sense? Makes sense?
Here we go.
Okay, yeah. Let me see if I can think of that thing up underneath it. Yeah, make it a little smaller. I can't think of that thing. Yeah, I'll get there. So anyway, so when you see me say memory, emotion, and pleasure, understand the interpretation of how you're feeling is up here, what you're gonna do about it. So it's a part of the memory pathway. you can't have no memory unless you got a working spinal cord or something. Makes sense, right? So what happens, it comes through here, a lot of this stuff is managed in here, and it's interpreted up here. That's how you can make a decision about, right? If I'm mad, am I gonna hit him or am I gonna be quiet?
So let me ask you something, Doc. So they say like, cause when they, when I used to play soccer when I was younger, they say that it ain't just our brain that have memory; it's also our muscles that also have memory.
Exactly.
Is that
Because
true?
you gotta bring the information for what the muscles are doing. And by the way, when you look at that parietal lobe right there, that's what takes in all the sensory information. So you can move your muscle to handle whatever's coming into you. So if it's getting hot outside, you take off, you take off a coat. If it's cold outside, you put on a coat, right? Whatever's coming from the outside, the sensory part from outside, heat, right? By the way, if you think about it, heat is energy, right? But in many ways, it's touch too. Understand that? Understand that? Because, if you're in the air has pressure and also has heat, right? So you gotta have the pressure to add the heat to really perceive the thing, just like if you put your hand on a stove, a hot stove, right? Like that, where heat comes at you slower, but it's pressure just the same. So your parietal lobe is picking up the sensation of heat, and then you figure out what you need to do, like go drink a cold drink of water. But your hypothalamus just told you, right? You hot outside, and what happens is the water in your bloodstream goes a little bit lower because you're sweating some of the water out through sweat. Makes sense, doesn't it? See how that works? But that's information coming from out here, interpreted in here. You go over here and make a decision. What's your best decision when the weather gets hot?
Get to the air conditioning.
Yeah, that's what you. Then you put your muscle coordination in gear to get somebody to play school. Makes sense, right? Right? And that's the whole thing. It's all connected. So no matter where we start, no matter what we put in these zip codes, there's a heat, let's say a heat perception pattern, right? There's a hunger perception pattern. There's a thirst perception pattern. You can see how they can all work together. All right, so in this.
It was the orbital frontal lobe.
Yeah, but I want to get the one that's underneath the corpus callosum. I need to see the corpus callosum because I can't think of the name. Anyway, there's something called substantia nigra, but it's in these. Anyway, I just can't remember right. All right, any other observations from this? From the thing. All right. So what I'm gonna do now is I'm going to give you an introduction to what we're gonna talk about next. Any questions about this, right? Any questions? So I'm gonna erase this and I'm going to introduce, and you all have heard it before. We're gonna look at, I'm debating, let me see. All right, I'm gonna erase this for the time being. Yeah, because I think I'm gonna erase it for the time being because I need some room to put some stuff on the board. We're gonna talk more about it next week. All right. Now remember, we say that the brain has structure and it has function. Okay? There is.
Here you go.
Yeah. Okay.
Lateral and corpus callosum.
Corpus callosum, they want to do part down below. They do the general thing. They don't show it from the front part. Let's see. They don't show it from the front part. Oh, there we go. Let's see. They still don't show what I want to show. That's all right.
All right, by the way, y'all got to see the video, the YouTube video. This is Paul Anderson. Get his thing. Okay, anyway, so here we go. Let's talk about the concept of psychology. And the reason why I do this is all of us are human beings with a brain. And there's some very interesting things that, you know, when we deal with things like recovery, counseling, all that kind of stuff, most of that's based on the concepts we come out of psychology. And it's broken up. Has anybody had Latin or Greek in school? All right. Anybody that had a little bit of that, this comes from the word what? Psyche. Now, psycho is what we call a vernacular term. You know? We understand what y'all talking about, but it ain't that accurate. Okay, psyche. All right. What does psyche mean? Those who had a little bit of it.
Psyche, I forget. I know what you're talking about.
Yeah,
I
yeah.
forget.
The brain,
Well, the brain helps
The psyche
construct
help-
this.
yeah.
the mind.
All right. Soul. I ain't got too much time. Soul. Okay.
Soul, okay.
You know, that's who you really are. Even though we're looking at how tall you are, short you are, you got a unique personality. Ain't nobody got what you have. You just different. Everybody. And that's your soul. Your essence of yourself is your soul. Okay. That makes sense, doesn't it? Yeah, kind of frou-frou, but does make sense, right? Okay. Then you have this part, logos, comes from the Greek word logos. What does that mean?
The universe.
Universe or knowledge of the universe. Knowledge. Soul, knowledge. Okay? Now, we haven't linked to the brain yet, but I'm gonna give you all a little bit of introduction so you can see how it's linked to the brain. If you didn't have no brain, you could not have any psychology. All right? When a person's comatose and laying out, ain't doing nothing, they ain't got no personality, they just there. They're a person, but you don't know what their personality is like, because everybody's personality is unique, right? Now, you know, even if you, in coma, you're unique too. Some of us are tall in the coma, short in the coma, young in the coma, old in the coma, right? But everybody in the coma, okay? So, everybody got a soul, everybody got some knowledge. Now, how can we get knowledge of your soul? What are the ways we can obtain, how can I obtain knowledge about the innermost self?
Become conscious of ourselves.
Now here's what I'm gonna say now. When you become conscious of yourself, what's going on for you to become conscious of yourself? Now, you know, babies are conscious, you are conscious, it's a different kind of consciousness, but it's a growing, developing consciousness. All right? So what is required for you to understand your own soul?
Awareness.
How do you get the awareness?
Love.
Say that again?
Meditation.
Say it again?
Meditation.
How do you know that you're meditating?
Knowledge.
Feeling.
Okay, now we're getting somewhere. There's a certain feeling you have when you meditate. Tell me your feeling when you meditate. Tell me what you feel when you meditate. Yeah, you do. Everybody meditate. They do it in their own way, and it may not be in a formal setting, but everybody meditates at some time.
Just going within.
I mean, you listen
What happens?
to
How
yourself.
do you feel? I'm talking about how you feel. How do you feel when you go within?
Calm.
Who said calm? Will that match? Does that word match the way you feel when you meditate? Does calm actually match it? If you don't, give me a better word. I feel calm when I believe I'm meditating.
Stressed.
What happens to the stress when you're meditating?
Peace. It goes down.
I hear it goes down and you get a little bit of peace about the thing. Those are feelings. Doesn't your brain help mediate feelings?
Feeling is.
Y'all heard about your midbrain, didn't you? Right. What are you gonna say?
Feeling is everything.
Feeling is okay, so is that marker a feeling?
You could feel it if you
You can feel it.
could.
Exactly. Can a marker feel?
Probably not.
Can a marker feel? If I hit you upside the head with that marker feel anything?
No.
You would. Markers don't say ouch. All right, just in case y'all didn't know that. So, you have a feeling when you meditate. The calm and peace fit that.
That's the goal.
Well, when you're heading from a traumatic place to a calming place, what happens to the trauma? What happens to that feeling of trauma?
If you go into a place of what comes.
Yeah,
is-
because obviously when you're
trauma
meditating,
and you,
right? You may not get to the place you want to be, but you ain't there. You ain't there.
you learn to cope with it, right?
Point is, you're learning how to have, let's just say, how to have a skill to cope with trauma.
You don't wanna cope with it, you wanna heal it. Let it go.
All right. When I sprain my ankle, it's gonna hurt till the hurt go away. I gotta deal with it while it's hurting,
Right,
but it ain't going away yet
to the heel.
till it fully heals. So you're getting to a goal of healing. There may be still a little bit of pain along the way, but the issue is you ain't where you was. The meditation practice is getting you there. The better you get in meditation practice, the more calm and peace you get. There's also reflecting the increase in dopamine and serotonin. So you see, you can actually change your brain chemistry by practicing meditation. But what do you do? How your muscles feel?
Relax.
Exactly. So there's a piece of muscle there's a piece, P-I-E-C-E, of muscle coordination that helps you relax. You still got some muscle activity, but you're relaxing, right? By intention. Which means when you relax by intention, you still have some muscle coordination with it because you can consciously choose on how relaxed you're going to be.
Is sleep a form of meditation?
It can be.
Okay.
Sometimes meditation will put you to sleep when you really need it.
Okay.
Especially if you intend to relax into a state of sleep. You can practice that. Makes sense, doesn't it? You see how we can put. Does it make sense? Wait, don't it make sense? Tell me if it doesn't now.
It makes sense.
All right. So understand this is dynamic. It ebbs and flows. Right? But understanding the whole brain is involved. Everything from making the decision to meditate, putting yourself in a relaxed position with voluntary muscle activity or less activity, right? You have a feeling of peace and calm. So everything is engaged. Make sense, doesn't it? See y'all next week. We'll talk more about psychology in the brain.
All right, Doug.